In section 3.6.3, we'll examine a specific application regarding spring motion. This comes with a new formula. Consider a mass attached to a vertical spring, set in motion, and allowed to oscillate. Now, if you'd like to visualize this situation, you can look at this diagram that we have down here. So we have a rigid spring attached to a base. Then we've attached a mass to that spring. When we do that, the spring will stretch a little bit and then come to rest in equilibrium position. So here, this horizontal line marks the equilibrium position of this mass. Now, if we come and pluck that mass or toss it up a little bit, it's going to begin oscillating. In the absence of damping forces, that mass is going to oscillate up and down indefinitely. This is what we call simple harmonic motion. And as you'll see, the position of that mass is dependent on a sine or a cosine wave, which is a periodic function. The position x of the spring at time t for a weight in motion is given by x equals v naught over omega, sine of omega t, plus x naught cosine omega t. So here, x is the dependent variable representing position. T is the independent variable representing time. All of the other variables in the formula are actually parameters. They're dependent on the specific situation. X naught is the initial position of the mass. V naught is the initial velocity of the mass. And omega, which appears in lots of different spots in our formula, is also a constant. This same equation can be used for a weight attached to a horizontal spring and set in motion on a frictionless surface, and we'll look at that one in example 5. Let's begin with example 4. A block hanging from a spring oscillates freely. If the block attached to this certain spring is given an upward velocity of 0.3 meters per second, this would be the initial velocity, or v naught, from a point 0.5 meters below its resting position, this is the initial position x naught, then its position at any time t in seconds is given in meters by this equation. So this is derived from this general formula. Our problem is to find the maximum distance that the block travels from its equilibrium position. So again, the mass is going to be oscillating up and down freely. If we were to plot its position versus time, you'd see that we would come up with a sinusoid, or a sine wave. That sinusoid is described by the given function. Notice the pattern of this formula. You have a distinct sine and a cosine wave. If you'll recall, a function of the form a sine of x plus b cosine of x can be condensed into the expression square root of a squared plus b squared times sine of x plus alpha, where tangent of alpha is equal to b divided by a. Recall, this is called our reduction formula. Cut. Three, two, one. A over B. Recall, this is called the reduction formula. So the current function giving the position of the mass at any time t is in this format. If we apply the reduction formula, then we can see that this coefficient would give us the amplitude of that sine wave. That is, it will tell us the maximum distance above or below its equilibrium position that the mass attains. So to answer the question, we simply need to find the amplitude of the resulting condensed sine wave. So in this problem, a is equal to negative 0.3. So we're going to find the square root of negative 0.3 squared. And b is equal to 0.5. So we'll add this to 0.5 quantity squared. Evaluating the squares, 0.3 squared would give us 0.09, and 0.5 squared would give us 0.25. If we add those together, we'll get the exact value of the amplitude, which is 0.34 under the square root. Let's go ahead and approximate this with the calculator. So the square root of 0.34, whoops, try again, square root of 0.34 is approximately 0.58. Recall that the linear distance was measured in meters in this problem, so we can say the maximum distance above and below the equilibrium position for this mass is 0.58 meters. Pretty simple. Let's look at an example of a horizontal model. Example 5 says a block is attached to a spring and set in motion. In this case, the spring is attached to a rigid wall, and the mass is allowed to oscillate on a frictionless surface. So if I pull it this way, the spring is going to pull on that mass and drag it back in this direction. As the spring is compressed, it's going to exert a force on the mass, pressing it back in this direction. So again, the mass is going to oscillate left and right indefinitely. When we're modeling this with a frictionless surface, we can say there's no damping forces present, and it will oscillate indefinitely. The position of that mass is going to look like a sinusoid when plotted versus time. For this block and spring, the location on the surface at any time t in seconds is given by x equals the square root of 3 sine t plus cosine of t. Find the maximum distance reached by the block from its equilibrium position. So recall that once again, the amplitude of the condensed sine wave is going to reveal this maximum distance. So applying the reduction formula and recognizing that the square root of a squared plus b squared gives us amplitude, that's all that we need to calculate for this problem. A in this case is the square root of 3. B is 1. The square root of 3 squared is 3. 1 squared is 1. Looks like we have a nice, neat, rational number here. Square root of 4 is 2. So if we were to apply the reduction formula to this function, this would be the amplitude of the resulting sine wave. Now, this problem didn't give us any units for distance, so we'll just say 2 units of distance to be clear. In this video, we were examining an application of the reduction formula to an oscillating mass. As you progress through your mathematics classes, specifically whenever you get to differential equations, and you'll probably see this in your physics classes as well, you'll look at more of the intricate details of actually constructing a model such as this. When you get there, you'll know how to handle that with your reduction formula.